All right, hello everyone. Welcome back to another one of Mr. Martin's math videos. Again, this is a video specifically for BC Pre-Calculus 12. We're on Chapter 8 looking at logarithms, and today's Section 3 specifically looking at the laws of logarithms. So here there's going to be some review from grade 9 and grade 10 when we were dealing with exponential laws, okay, or exponent laws. If you remember some of those, the product of powers and the quotient of powers, the power of powers, all those exponent laws. How do we combine exponents? So here, because we know that exponential, or the logarithmic function is the inverse exponential function, we can know that some of these laws are going to have their own form in logarithms. And so those are the laws, and we'll kind of look at the proofs that are anchored in those original exponent laws that we looked at in grade 9 and grade 10 as the proofs for these logarithm laws. So let's look at the laws. Let's jump right in here. Law number 1, the product law of logarithms. Okay, so what the product law of logarithms says that if you have a log c m times n, it can be split into log c m plus log c n, okay, and vice versa, right? These are two-way streets, all right? So it is true this way as this way, okay? So that's one of the laws here, all right? Proof is essentially in this situation here. So let's let log cm equal x, all right, and log cn equal y, all right, where m and n and c are positive real numbers. C is not equal to 1. So write the equation in exponential form first, all right? So of course we have the m1 c to the x is equal m, and then c to the y is equal n, all right? Now if you multiply those two together, m times n, you're essentially multiplying c to the x times c to the y, which using this is a product of powers exponent rule here. So we would have this going on c to the x plus y, and then putting into logarithm form, you'd end up with this situation here, okay? And then we know that x and y, originally we substituted log c to the x. So log c to the m is equal to x, and log c to the n is equal to y. And so x and y can be substituted back with those, okay? And then we've proved that those are indeed equal on both sides, okay? And then log number 2, again, is based on the quotient of powers law, but it's the quotient law of logarithms, okay? And it just says that log base c m over n is equal to log base c m minus log base c n, okay? And again, these are two-way laws, right? They work, back and forth. And the proof is similar. Essentially, again, you're using that quotient of power law here to prove the logarithmic law, okay? So make sure to take a look at that. Make sure you understand those proofs. So now let's start applying. Oh, sorry, one more law here. We're going to learn all three of them right off the bat. The power law of logarithms. This is the one that's based on the power of powers law in exponents, okay? And it simply says that log base c to m to the p is equal to p times log base c to the m. And again, two-way as true one way as the other way, okay? So in some of these questions, you might have to go to the right or to the left in these laws to solve your problem, okay? So you have to use different strategies. And again, you'll recognize the exponent law, power of powers law in its proof as you move through that, okay? So let's see it all in action. So expand each expression so that x, y, and z have exponents of 1, also make sure x, y, and z are in their own logarithms. And here we need to split these up. All right, so because these are all multiplied together, okay, I can split these up into log base 7x plus log base 7y cubed plus, log base 7 square root z. Okay, and so because of the first law that we looked at, the product law of logarithms, I can split all of these up because these were initially multiplied together. Okay, if you wish, brackets. Okay, now the question also tells us to make sure to give an exponent of 1 here. So that means the first one's fine because this one already has an exponent of 1, right? The x, but the y and the z have an exponent of 3, and the z has an exponent of 1/2. So a log, the first one doesn't change, it's fine, okay? But because of the power law of logarithms, that 3 I can make as a quotient of the log function here. Okay, essentially this goes in the front. All right, and same thing with this one. Now I can change z, square root z to z to the 1/2, right, and then bring that forward. Okay, and that's what I'm going to end up here doing. And so it's 1/2 log base 7z. And that would be your final answer. Okay, I've fulfilled everything in the question there. All right, another example here using some of the other laws here. This is going to use both the product law of logarithms and the quotient law of logarithms. And so here I have log base 5x plus log base 5y. Okay, and then because it's divided by z here, it'd be minus log base 5z. And that would be it. It's as simple as that for that one. Okay. And then last one here, again, I understand that this is log base 7x to the 1/3, right? Putting a root as a rational exponent. Okay, and then from there, I'm going to move the exponent in my logarithmic function as a quotient in my logarithmic function. All right. And so those are 3 examples there. All right, go ahead and pause the video and try these 3 on the right on your own, and then unpause when you feel like you're ready to see the answer. All right, so let's take a look here. Here, the bracket, this exponent of 8 is on all 3 of these, and so essentially the bracket would be, so that if I just took care of the inside here, it would be log to the 5x plus log to the 5y plus log to the 5z. All right, and because that exponent of x is on all of them, that coefficient of 8, that exponent of 8 would become the coefficient. So it'd be like 8 log 5x plus 8 log 5y plus 8 log 5z. Okay, if we were to distribute that. Okay, next one here, I have log to the base 6y minus log to the 6x squared. And of course, because that exponent here, I'm going to put that as the coefficient, I get log to the 6y minus 2 log to the 6x. All right. Last one here. I'd have log, and here that I have no base, so it's a base 10. Okay, I can just not write it. Log to the x cube minus, I don't know why I wrote that, log to the y, and then also minus. Okay, you have to understand that even though there's a multiplication here between these two, here, I'll do this. I'll show you guys this. So here, this would be bracket minus bracket log to the x plus log to the z exponent 1/2, right, instead of the square root. And then close that bracket, and then that negative would distribute, so you'd end up with, and then of course, let's move our exponents into coefficients based on the power of logarithms, and I get 3 log x, minus log y minus 1/2 log z. Okay, and that would be your final answer. Okay, so these are in your formula sheet, okay, but make sure that you know them, because the more you have to refer to them on the test, the slower you're going to be in getting through the questions and being able to finish the test on time. All right, let's move on to the next page. Example number 2, use the laws of logarithm to evaluate the expression. So here, I'm trying to use these laws here to figure out a way to solve these questions without using calculators, essentially, okay? So what can we do here? Okay, well, first let's separate these into separate laws based on the product law rule there. Okay, so product law of logarithms. So I get log 7 to the 7 plus log 7 to the 7 raised to the 1/2. Okay, so far so good, right? Log 7 to the 7 is 1. Okay, if you want to double check that, there's a couple ways. First, you can just put it into your calculator, right? Log 7 to the 7. Okay, you can also think about putting it back into exponential form. You have 7 to the x is equal to 7. Well, of course, x is equal to 1, right? And so either way, you're getting your answer. So this becomes a 1, all right? And then plus, now, of course, this is going to come up to the front. It's going to be 1/2 times, and then again, log 7 to the 7 is equal to 1. So 1/2, okay? And so I'm going to get 2 over 2, or 1, changed into a fraction with a common denominator, plus 1 over 2 is equal to 3 over 2, and that would be your final answer. Okay, so we use our log rules to get an answer, okay, by expanding our expression. Okay, sometimes it's going to be useful, though, to bring our expression together, because here, the 8, the 9, there's no real clear here, 7 to the 7, it was clear that, those were 1, and we were going to get good answers from that. But here, these ones don't really work this way. However, this one, it's going to be better for us to go from right to left in our exponent rules to solve for this one. All right, so I'm going to change this to log 6 to the 8 times 9 divided by 2. All right, and so log 6 to the 8 times 9 divided by 2, so 72 divided by 2 is 36. All right, and at that point, you can imagine that, change it to exponent form, or, just simplifying it further, log 6, log base 6 to the 6 squared, right? And then it would be 1 times 2, which is equal to 2, okay? So in this situation, it's equal to 2. So it'd be 1 times the 2 in the front. Okay, another way is here, change this into, so 6 to the x is equal to 36. So what would x equal? Is equal to 2, right? And so our answer here is 2. All right, same idea here. All right, so I'm going to have, and again, I want to move this back here as the exponent of 12. So I'm going to get log base 2 of 12 squares is 144 divided by 6 and then the exponent of cube root of 27 is 3. Okay, so it'd be 6 times 3 times 3. Okay, I get the 6 from here, and I get the 3 from 27 cube rooted, or with an exponent of 1 over 3. All right, that's going to give me a log 2 to the 8, okay, and then and then to get it log equal to 1, the base and the next number that you're logging has to be the same, right? So log base 2 to the 2 to the 3, right? And then that 3 can go back to the front, and I would get 3 to the 1, which is equal to 3, okay? Or again, you can think about it in exponential terms. 2 to the x is equal to 8. X is equal to 3, right? In this situation, if I were to use x to represent the value of the logarithm. So that's the answer there. So again, pause the video, give these questions a shot, and then unpause when you're ready to go over some of these. All right, hopefully this video went well for you. Let's take a look at some of these problems here. Again, sometimes it's better to expand, sometimes it's better to separate, depending on the situation we're in. Okay, so log 3, I'm going to split these up into log 3 to the 9 plus log 3 to the 3 square to the 1/2, okay? And then I'm going to switch this to log 3 to the 3 squared plus log 3 to the 3 to the 1/2. Okay, now bring these exponents as coefficients. And then these equal 1, right, without the coefficients. So I end up with 2 to the 1 plus 1/2 to the 1. Okay, and so my answer would be 2.5, or 5 over 2. All right, another problem here. Just going to set this up here. Log to the 5, 1,000 divided by 4 times 2, right? No other exponents or deals here. So 1,000 divided by 8 is equal to log 5 to the 125, okay? And then so here, log 5 to the 5 cubed. And hopefully by now you can recognize that that equals, the value of that would equal 3, right? This would go to the front, and you'd get 3 and then to the 1, because this is equal to 1. And one more problem here, again combining things. I'm going to be moving this back into its an exponent position here, the 1/2 here, and going from there. So I have log to the 6 squared, so log base 3 to the to the 36 divided by square root of 64, which is 8, and then plus 2. So that multiplied by 2 would actually be on the top, okay, because it's a plus, not a minus. The minuses go on the bottom, the negatives go on the bottom, positives go on the top in this, okay? And that is equal to, if you plug it all together, log 3 to the 9, okay, and then log 3 to the 3 squared 2, because this is equal to 1, right? And then the 2 is brought to the coefficient. Final answer. All right, so hopefully those are becoming more familiar for you. Okay, hopefully those went well for you. Now let's use these laws to simplify some more expressions, specifically dealing with some binomials and trinomials in some algebraic kind of setting here. So let's take a look at some of these. So write each expression as a single logarithm in simplest form. Make sure to state any necessary restrictions on any variable you have. Okay. So let's start off by putting this into a single logarithm base 7 kind of expression here. So I have log to the 7, and then this is x squared plus x, which is times x in my, this is all in the log bracket, right? And then don't see this as 5 log 7x over 2. See this as negative 5 over 2 log 7x. Okay, so that becomes a root or an exponent on that x. So divided by x to the 5 over 2. Okay. Now here, those restrictions that they're talking about, again, we can't, because we have a fraction with a variable in the denominator, we have a restriction that x must be greater than 0, right? Restrictions, x must be greater than 0, because if that x on the bottom is less than 0, then we're going to end up with undefined term. All right, so let's keep going here. So it simplifies to log base 7, and this turns into x cubed, right? X squared times x over x to the 5 over 2. All right, and then again, using our exponent laws, we can, in this situation, log base 7, because I can use my exponent rule inside of that bracket, right? So this ends up being x to the 3 or x to the 6 over 2 minus x to the 5 over 2. Oh, no, sorry. Just minus 5 over 2, which gives me a final answer of log 7 x to the 1/2. Okay, and then you can bring that as a coefficient 1/2 log 7x. Okay, that would be your final answer here with your restriction here. All right. Okay, let's try this one likewise here. So minus that. So also here you're going to want to factor these because we're going to be setting up a rational expression within our log bracket to simplify, right? So this is going to give me on the numerator, it's going to give me log 5 to the 2 bracket x minus 1, right? That's the factored form of 2x minus 2. And then here, this factors out to, what, x plus 3x minus 1. So this would be over x plus 3 and then x minus 1. All right, again, restrictions. X cannot equal negative 3 or 1. All right. And then we can, once those restrictions are done, we can cancel out and we get log base 5 2 over x plus 3. And that would be your final answer there. Okay? So that's how I'd use it in situations where there's some algebra. You can, cancel rational expressions. You guys know how to do that. All right. Let's look at some problem solving here with some word problems here. So the human ear is sensitive to a large range of sound intensities. Scientists have found that the sensation of loudness can be described using logarithmic scale. The intensity level, beta, in decibels of a sound is defined as beta is equal to 10 log I over IO, where I is the intensity of the sound in watts per second meter, and IO is this value, 10 to the negative 12, corresponding to the finest sound that can be heard by a person of normal hearing. Okay? Audiologists recommend that people should wear hearing protection if the sound level exceeds 85 decibels. This is approximately how loud a chainsaw is. The maximum volume of a pair of portable headphones is 110 decibels. How many times as intense as the sound of a chainsaw is the max volume setting on a pair of portable headphones? Okay, so we want to know what the difference is here. So of intensity. So we're looking at beta. If we want to find the difference, right, where the difference is a subtraction. All right, so beta, let's say of the louder one minus a smaller one. Okay, and if we were to set this up using our log, here it would be 10 log intensity 2 over that faintest sound minus 10 log intensity 1 over that faintest sound that people can hear. Okay, and then we're finding the difference of obviously on both sides here. So I'm going to substitute the maximum of the headphones, which is 110, and then that's going to be minus 85. All right, and I'm going to, on this side here, I'm going to substitute I2, I'm going to find the intensity first, over 10 to the negative 12 minus 10 log I1 over 10 to the negative 12. All right. So this is going to be 25. All right. And here, because there's minus each other, I'm going to be able to divide. So here I get 10, and then log I2 over 10 to the negative 12 over I1 over 10 to the negative 12. Okay. Now at this step I can do two things. One is I can divide both sides by 10. And the other one is I can, multiply by the reciprocal to subtract these fractions. So here I get 2.5 is equal to log I2 over 10 to the negative 12 times 10 to the negative 12 over I1. Okay, and then these obviously cancel out. So I get this setup here of 2.5 is equal to log of intensity 2 over intensity 1. Okay, then I can change this into exponential form, right? Because there's no base here, I assume that my base is 10. And so 10 to the 2.5 is equal to I2 over I1, right? And that's the ratio we want. How many times more intense is I2 than I1 is essentially this fraction here, dividing by 2 and I1, and the answer then would be 10 to the 2.5. Okay, and if you want to know what that is, it is 316 times more louder. Okay, the 110 decibels in your headphones. So it's not a linear function. It's like the Richter scale. A small change in decibels is actually a large change in magnitude. All right, and for B, sounds that are more at most 100,000 times as intense as a whisper are considered safe, no matter how long or how often you hear them. The sound level of a whisper is about 20 decibels, What sound level in decibels is considered the loudest possible safe sound for a human ear? Okay. What sound level in decibels? Okay, so first we got to figure out the intensity of the whisper, right? So I'm going to take 20 is equal to 10 log I of a whisper, right, over 10 to the negative 12. All right. Divide by 10 on both sides. That gives me 2 is equal to log IW minus log 10 to the negative 12. Okay, now here, remember that base is 10. So I have 10 and 10, and then I have negative 12. And so what I get here is I get 2 is equal to log intensity of a whisper minus negative 12 by moving that to the front. And then because it's log 10 to the 10, that equals 1 times 1, which is log plus 12 log. Okay, so algebraically, I want to bring that to the other side. So I'm going to subtract 12 on both sides. And that's going to be negative 10 is equal to log I whisper. And then I can change this to exponential form here, which would be 10 to the negative 10 is equal to the intensity of a whisper, or 1 over 10 to the 10. That's the intensity of a whisper. Okay, now I can use that to figure out how many times more, right? And so if it's 100,000 times more, that is 10 to the 5 times 1 over 10 to the 10, which is equal to 10 to the 5 over 10 to the 10, or 10 to the negative 5, okay? And so if I go backwards then, I can put this negative 5 into my equation of log now intensity, maximum intensity, max, minus, log 10 to the negative 12. Okay, and I can again work my way and plug that back into my same equation. Again, I'm going to subtract a bit of a blank here. Oh, okay, so here it's just which becomes negative 5 is equal to log of, I am over in order to get back to this, I need to do plus 12 on both sides, right? And then turn it back into a log of 10. So that's where that's coming from there. And so that becomes 7 is equal to that, and then over, okay? And in order for me to get back into an answer that is 10 log and intensity max over 10 to the negative 12, I need to multiply both sides by 10. And that's going to give me 70. Okay, so 70 decibels would be your answer there. All right, tricky question. I think it's in the textbook as well, if you want to double check that. But otherwise, your homework is at the bottom here. Due Tuesday. If you have any questions, leave them in the comment or in the homework question section. And we'll see you next time. Goodbye.